Welcome. My name is Hawk Jones, and I'll be the moderator for this Engineers Without Borders webinar, Water Supply Part 1 of 3, Source Selection and Development. This presentation is one of the core programs in the expanding series of online, on-demand continuing education programs created by Engineers Without Borders USA and presented by Contract Solutions Group. Before I turn the program over to our presenter, I'd like to make a couple of announcements regarding the program. As the program begins, you will notice the program itself will fill the majority of your computer screen. On the lower left of your screen, you will see a Pause Play button. If for any reason you need to pause the presentation, click once on the Pause button. To restart the program, simply click on the Play arrow that will appear in the same place. If you need technical assistance, please click the email link for client services at Contract Solutions Group located on our website pages, or you may call us for assistance from 7 a.m. Pacific Time until 4:30 p.m. Pacific Time, Monday through Friday. If you're disconnected from the webinar due to local internet issues, simply log back in through the Engineers Without Borders website and restart the program. After the program, you'll be taken directly to an attendance reporting page. It is very important that you complete this short form and submit it immediately upon completion of the program to receive full credit for your participation in this program. If this step is bypassed, neither you nor your chapter will receive credit. Now it's my pleasure to introduce our presenter for the program, Kelly Latham, Project Manager with EWB USA. Kelly earned her BS in Environmental Engineering from Northwestern, earned her Master's in Watershed Science from Colorado State University, and spent 2 years in the Peace Corps in Honduras as a water and sanitation engineer, where she designed and oversaw construction of numerous rural drinking water systems. Prior to the Peace Corps, she spent 8 years with an environmental consulting firm on various water resource projects focused both on protection and remedial design. Her extensive field knowledge and unique perspective enables her to provide insightful guidance and technical assistance to the volunteer chapters throughout the assessment, design, implementation, and monitoring process to ensure that the EWB USA projects are sustainable and of high quality. Kelly, I'll turn the program over to you.
Thank you. Welcome to this first presentation for a three-part series in water supply. Today, the discussion will be focused on source selection and development of EWB USA water projects. The purpose for dividing this out into 3 different presentations is just because of the complexity and extensive nature of water supply systems. And so really the first presentation that I'll go over today is going to just get you started on any kind of water supply project that you're working on, to think about on your first assessment trips and as you're making some of the preliminary decisions before you go down the path of a detailed design. So let me back up for 1 second and just highlight how this water supply webinar fits into a larger program that we have of various technical webinars that we're either currently preparing or have prepare over the next year. So if you look at this matrix, along the left-hand side, there's several different webinars that we plan to record, and along the top, the column headings, there's various EWB USA project types. And so depending on what type of project, so in your case, if you're working on a water supply project, you would look on that highlighted column down the row and see all the potential technical webinars that might apply to your project and that you're encouraged to participate in as they become available. So like I said, this webinar is focused on the water supply projects, the first part, source selection and development, and the specific goal is to assist project teams with the selection of a water source and the assessment, design, and implementation of the infrastructure needed to make that source more available. The outline of this presentation will start off with just an explanation of why safe drinking water is so important, to provide a little context for water supply projects at EWB USA. Some background information of what we're talking about with typical water supply projects in a developing community setting, such as EWB USA, versus what you might think of as a water supply system in the U.S. We'll go over different source options to be considered and how to identify and select the best source option for your project. Some design criteria for developing different sources, whether it's a dam, spring boxes, rainwater catchment, well installation, or pumping's needed, whatever, to actually develop that source so that it is accessible. And then I'm going to finish off with some lessons learned based on the experience we have as an organization implementing water supply projects. And then lastly, there's just a slide that has some reference information that will hopefully be useful as you're working on your water project. And just to make sure we're all focused on exactly what this presentation will focus on, I wanted to just highlight the things that will not be covered in this presentation and where you can go to get some of that information. So we're just going to be talking about the actual source itself and not the distribution infrastructure, so any pipeline that might be needed or any of the storage infrastructure such as tanks. And that is what will be covered in that second part of the three-part series titled Distribution and Storage. And then water treatment is that third piece, and so if you really have a project focused more on treatment, it would be important to see that third webinar, which focuses on water treatment. I'm also not going to have time to really go into the details of the designs themselves of the infrastructure that we'll go over today, such as wells, spring boxes, and dams. I'll be going over some design considerations of each of those features, but not really walking through exactly how to go about the design itself. Water testing is also something that's provided in another resource, and that is our water testing guidance sheet, which is available on our website under the project resources. There's a link for EWB USA technical guidelines, and in that you will find the water testing guidance sheet. And then lastly, I'm not going to go into much detail about our overall project process, specific to the different forms we have as you're working through your water project. And there are some other webinars that hopefully you've seen on this as part of this webinar series that you can get that information from. So to start off, why is drinking water, safe drinking water, so important? And I think that's probably obvious to most people listening to this presentation right now, since you are working on an EWB USA water supply project. But here's just some statistics to kind of have in your mind, put out by the World Health Organization, just to provide a little context to what we're trying to do here. And the big thing specific to water supply is that 1.1 billion people have no access to any type of improved drinking water source. And consequently, the subsequent bullets highlight the huge populations that still are susceptible to various diseases, and some that lead to death. 1.6 million people die every year from diarrheal disease, and then 160 million people die or are infected with schistosomiasis, and some of those people, it could become so severe that it would result in death. There's some other statistics there as well. This was accessed back in May of 2009, so I imagine since we originally put this presentation together that some of those statistics have increased, but in general that situation has been the same for a long time, such that it prompted the various organizations to put together the Millennium Development Goals. And there's a variety of different goals out there, known as the MDGs, that relate to poverty in general. And where water supply fits in is that there is a goal that to have, by 2015, the proportion of people without sustainable access to safe drinking water and basic sanitation. And we're hoping organizationally that EWB USA will be able to contribute to that huge, large goal that various nonprofit organizations and other NGOs are also working on. But that kind of provides the context for the purpose of working on these water supply projects with EWB USA. So to give a little background on what a typical water supply project might look like at EWB USA, I just want to go over a few pictures that we have of various projects. The truth is that the nature of a water supply project with EWB USA can vary extraordinarily. Sometimes, you're really just focus on improving the accessibility to prevent the situation, which is very common in these pictures where you see, children and women walking to some distance to collect water and then carry it back, on their heads. And then trying to get that water so that it's more accessible. Maybe not a faucet inside the home with a kitchen like you would expect in the States, but at least a tap that's closer to their home, maybe in a central location in the community or maybe in each household depending on the specific needs of that community. Or it might be a project where you have this open well here where you're dipping a bucket down to collect water, which I think might be obvious could introduce a lot of contaminants, and you're improving that access point by sealing that and having a drilled well with a hand pump so that there's no risk of contamination entering at that well point. That in and of itself might be what the water project that you're working on consists of. Some other examples. We have here a project where if you look here, this is, there's already a earthen dam kind of built up to collect some water, but as you can see, it looks pretty susceptible to failure, and so the project might be just improving that structure with some sort of concrete catchment area. This is not the same project. As you can see, the terrain is quite different around it. So the project also might be abandoning this source altogether, considering if you look around, it looks like this might be highly eroded area, maybe pasture land, and so it's changing the source to a location that's more protected and then building a more appropriate concrete structure to capture that water. Or you might have a situation that's common with EWB USA projects. You're in a situation where you don't have access to drilling wells and there are no mountain springs in this nice protected forest, and really the only water source is this river that's pretty contaminated. And so the project is to simply construct these biosand filters so that you can take this dirty water, put it through this filter, and have clean water for drinking. So those are just some examples to kind of highlight what kind of projects we're talking about when we talk about a water supply project at EWB USA. So these next slides, hopefully this slide isn't confusing. It's intended to simplify what really is quite complex when you think about all the different components and variables and decision-making points for various water supply projects. And so this is an attempt to simplify that a bit. And so one thing to keep in mind is that depending on your community and your situation, you might be talking about a household scale model for water supply versus a community scale model for water supply. And so to highlight that difference, both models have a source. And in the household model, we're talking about those last two pictures from the previous slide, where somebody's still having to go manually collect that water, and that's usually what the distribution consists of versus any piped infrastructure. And then that water is treated, but in a point-of-use treatment type of situation. Individual biosand filters in your home or boiling water in the home, and then the water is kept in small containers in their home for their storage. There's no centralized storage, and that's in comparison to a community scale model where you might have you have the same source area, and then you're going to have some sort of piped system, typically to a treatment system next. And then that's a centralized community scale treatment followed by some large storage container, and then from there the water is distributed to potentially connections in each home or community taps or however. And so the order of the treatment, storage, and things might change a little bit, but the main thing here is to keep in mind that all projects have these four components: some sort of source that you have to identify, some sort of treatment, and maybe that treatment is just protection of the source, or maybe it's continuing for people to boil water in the home, but usually some kind of treatment is necessary so that it's drinkable. And then some kind of storage, whether it's containers in the home or a concrete storage tank, and then some kind of distribution, whether it's people walking to collect waters and you're improving the container they do that in, or it's an actual pipe system. And so it's a lot to cover to kind of consider these different models and the different aspects of each one and all those decision-making points. And to just highlight again, what we're talking about today is just these first couple boxes. All the rest of the stuff will be discussed in those subsequent presentations. So with that, let's talk about, well, I guess I just explained this. There's the second part of this three-part series is the distribution and storage, which are highlighted now, and then lastly, the treatment. So I think that should be clear at this point. So let's talk about what different source options are typical for water supply projects. And we've divided them out into three basic types. Your surface water source, which can be rivers, streams, lakes, and reservoirs. Groundwater, which is probably the most common water source for EWB USA projects, just because it's a better chance for that water to be a little cleaner, requiring less treatment, which hopefully will be more affordable in the communities where we're working. And so groundwater is both, a well situation like this, or I don't know if you can see as well in this picture, some sort of spring where the water is actually daylighting, so it's above ground when you access that point, but it is a spring fed by groundwater. And then lastly, the atmospheric water, so that's either a rainwater catchment system or some sort of system to capture fog and create a water supply through that. So in general, there's just some inherent advantages and disadvantages to each one of these water sources. What is most appropriate in your particular community is a very community-specific situation. So this slide is not intended to suggest you can just generalize this information. But just before we get started with the more specifics and how you analyze those different source options, I wanted to just kind of go over some general pros and cons. The surface water is a lot of times easier to access because you can see it, and sometimes it's a source that maybe is at a higher elevation, so there's more opportunity for some sort of gravity-fed situation. And so those are all good things. And then the challenge with surface water is that a lot of times it's contaminated, and it's extremely hard to protect surface water so that it's not contaminated. So most often it will require some level of treatment. The next option is the groundwater. And so groundwater, like I said, is probably one of the more common sources of water for EWB projects because it doesn't have as much of a treatment need. So generally it's easier to protect those sources requiring less treatment. However, the problem is, especially in the case of a well where you're having to drill below ground, it's very hard to assess before investing into the actual drilling effort to know what the quality of that water is. So it might not have a lot of human contaminants, but it might be a groundwater or an aquifer that has a lot of arsenic in it, which would be a problem. And so it's hard to characterize with respect to water quality, and it's also hard to get a sense for what kind of pumping rates you can expect to get if you were to drill a well and pump water from that aquifer. So it's much more difficult to assess, so it's a little bit more of a gamble. And then except for the situation where it's a high mountain spring fed by groundwater, other than that situation, you're going to need some sort of energy to pump that water, even, whether it's a hand pump or an electric pump, some sort of energy is required, and that pump is going to have some limitations because it's moving parts that are harder to maintain and have more expenses associated with it. And then lastly, atmospheric water can be a great clean source of water that's very easy to access if you're in a region where it rains year-round. A lot of communities where we're working, there are some very prominent dry seasons where it might go months, 3 or 4 months at a time with not a single drop of water. And so that's obviously going to be limiting with the atmospheric. Or just the storage requirement needed to meet that demand through that dry season would be hard. Or it's a situation where you're in a community that doesn't have, all the roofs are thatched roofs, so there's no structures to even capture that water to begin with. All right. So as you're assessing these different source options, here are a variety of different factors to look into. Water quality and quantity are the two most important things, and usually where you kind of start your analysis of your source options. And I'm actually going to go into a little more detail on those on the subsequent slides. But the other key source selection factors are the elevation of the source, simply knowing, are there any source options out there that provide for a gravity-fed option where you don't need any pumping? So are they at least 10 meters above where you need that distribution point to be? Distance is another thing. Maybe there is a gravity fed source, but it's over 10 kilometers away, and so it's not feasible for something that large, or maybe for your chapter that is something feasible. I don't want to set any hard limits for how far you should look, but I would, sometimes just the distance alone is too much, just considering the capital cost and the ability for the community to go and visit that source area and make sure it's clean. Water rights and land ownership issues are huge. They're hugely important as you're considering different source options. There might be a perfect high mountain protected spring that's nearby, but it's owned by somebody that will not give permission. And if that's the case, you simply cannot move forward with that project because of the risks. I know I personally was involved with the project where supposedly there was, the landowner had signed something saying they were okay with it, and I think had changed their mind later on and actually came out and threatened the people working on the construction of that water system when they were actually out there on their land. So land ownership is hugely important because you don't want to get down the approach of all the fundraising's done, you're out ready to construct, and then there's this challenge that you can't get around and you have to cancel the project. Source water protection opportunities is also important to consider. Sometimes you might have different source options and they're both kind of degraded, they have their water quality problems, but one of them is such where there's the potential for that area to be fenced off and truly protected, where the other, there's plans in the community to build houses up gradient from that source. So that's also important to consider. The economic situation in the community is really important, and when I review projects, and I've probably done 500 reviews since I started working here, I think one of the most common oversights for teams is to not consider the economic situation until they're later on in the design, and so they end up with a solution that the community simply cannot afford to maintain, let alone make any kind of repairs or upgrades, but to simply pay the electric bill, for example. If you're designing a project that requires pumping, you would need to know up front, before you get very far, as you're in your source selection process, the first step of water project, you need to have some sense for what the community could afford to pay to know what kind of electric bill you could even consider as part of your project. And then also just the inherent technical feasibility of developing a source. The rainwater catchment example, if you have a community with all thatched roofs and there's not the potential for that improvement of the roof, then rainwater catchment's not going to be an option, just technically speaking. So these next slides are going to go into a little more detail on the quantity and quality. So quantity, what we're talking about with quantity, it's the supply-demand analysis. And this is something that needs to be abundantly clear at the beginning of any water supply design. As you're proposing to invest money to improve some water supply source and make that more accessible, you need to understand if that investment is going to result in a fraction of the community having water for a fraction of the year, or it's going to be a system that's going to provide more water than they'll need even in 20 years down the road. And so in order to know that, you need to do a supply-demand analysis. So the supply side of that analysis, depending on your water source, you would have to measure what that capacity is of that source. So if you're talking about a spring or stream, what you need is the dry season flow, and it's so important that it's the dry season flow. I worked on a project in Honduras where there was a water supply system, and the design was done before I got involved, and then I was there to just oversee the construction. And so we were going to go out and just stake out the line, and the money was all raised, construction, people were contracted, everything was ready to go. And when we went out to stake out the line, and I was visiting the source for the first time, it was in the dry season, and the location of where in the stream where the water was going to be collected with a spring box had completely dried out. And so and this was a big project, I think it was $80,000, 3 different communities were going to benefit from it. And the source had dried up after all of that information had been collected. In the rainy season, there was so much flow, no one thought that they even needed to worry about it, but because the people doing the design hadn't been there in the dry and wet season to understand those fluctuations, it was a huge problem that required quite a bit of rework and redesign and having to fundraise over again because of that. And so understanding what that situation is in the dry season is essential for doing the capacity side of your supply-demand analysis of a spring or a stream. For a well, this can be a big mystery until you do some drilling, but sometimes you can visit nearby wells or talk to drillers in the area who have some experience to get some sort of estimate before you even drill that well at your particular site, to get some idea of how much you can pump. What is the recharge rate of the aquifer? If you pump at if your demand is 50 gallons per minute, and when you pump at 50 gallons per minute, the aquifer, draws down significantly, the water levels are decreasing and the well dries up. You need to understand what the capacity of that is compared to that demand. So you need to do some sort of recharge test, or get at least some anecdotal information from other wells, talking to other people with wells in the region or local drillers. Rainwater, if you're doing a rainwater catchment, you need some precipitation data. You need to be able to understand how the rain fluctuates throughout the year and what you can expect in a given month, so that you can understand if it even has the potential to meet the demand if everything was designed appropriately. And I think this last point I already highlighted with understanding the seasonal variation. It's just so important to not base your whole design on one measurement from your one assessment trip that happened to be in the rainy or dry season. It's important to understand how that source varies throughout time. And then the demand side is figuring out what that average daily demand is for the community. And that's really going to vary. I wish I could just give you some number to use, but it's going to vary based on the country and the practices with water and what the intended use is. So here's a range that I have, which is 20 liters per person per day if water is going to be used for only drinking and cooking, so things that you're actually consuming, up to 100 plus liters per person per day. If you're also going to be using that water for laundry and other household chores that are that use a lot of water but doesn't necessarily require the same level of quality, these are kind of the ranges. And so what you find, I think I've worked on or done reviews for projects in dry areas of Kenya where this value is used because the community would never dream of using the water from this system for anything beyond just for drinking and cooking. Versus, gosh, in Honduras where I was, this was the expectation because that was one of the main reasons for a water supply system, is that women didn't have to walk far to do laundry in these streams or access points that were far away. And so getting that water closer, assuming that there was a source that was enough, was important, and so that needed to be what that per person demand was. So it just depends on your community. The important thing is to understand what the expectations of the community are, what's feasible, and then communicate what the outcomes of the project would be. And then it's also really important to consider that future growth. If you're hoping that this project is going to last 20 years, you need to understand what that population is going to be in 20 years. In some developing communities where families are still having 4, 5, 6 kids, that population growth is pretty extreme. And in 20 years, the population might double. And so it's very important to be very well aware of that so you can ensure your project has the potential to be sustainable. On the quality side of things, again, it's important to understand that intended use. Occasionally, there's a water project where the intention is not to use it for drinking water. It's for bathing or some other use because maybe they already have a decent system for drinking water. So if that's the case, the water quality is maybe not as important or doesn't need to be at as high of a level. That's pretty uncommon. Usually we're talking about actual drinking water. But it's important to consider. And then, of course, just doing some visual observations can help narrow down source options before you go to the next step of doing actual water quality testing. It's also really important to consider the watershed or the recharge zone and what that looks like. You might be there in the dry season where there's not a lot of runoff happening, and so there's not a lot of contamination at your source, but you can see that it's pasture land, and so you know that there's there's cows that would be a source of bacteria pollution to your source. So maybe they're not there right now, or there hasn't been runoff or rain event to wash it into your source area, but you can kind of make some assumptions of what the water quality might be just based on that, and it's important to consider that in addition to, you know, a sampling event. That's just one point in time. And then with that goes hand in hand the community's capacity to actually treat that water. If there's really not that capacity within the community to be able to sustain some sort of treatment system, then having a clean source is going to be a really important factor in your evaluation. And then again, water quality testing is always going to be a first step as you're justifying the selection of a source. And I'll go into some parameters that you should look for in subsequent slides. But again, I'm not going to go into too much detail because we do have a water testing guidance sheet that you can refer to. So here's just an example. I don't want to spend too much time on it, but this is an example of a calculation that you might do for doing your supply-demand analysis. And this is not intended to be the one and only way to do this analysis, but just to give you an idea. This is for a gravity-fed system. I think this might have been an example from a project that I worked on previously. But in that community, the population growth rate was 3.5, and that was based on some local information on census data about what to expect. You have your present population, you specify your design life, and then you can calculate with just some simple growth rate formulas what that future population means. This I think is the arithmetic formula. There's a couple different formulas you could use. This is what was recommended for my specific community that I was working in Honduras. And then you figure out what your assumed individual daily demand. So in this case, this would translate to about 100 liters per person per day. So it was that higher end of it, and then you figure out what that demand is. So on a daily basis, your average daily demand is 15 gallons per minute. So that means we need to find a source that supplies 15 gallons per minute so that it can meet that average daily demand. Even if you have storage in your system, if you can't meet that average daily demand, then you're always going to have problems with, with certain people not having access to water. So water quality, here's just a little bit more information, but again, not too much detail. The type of analyses you should run is again going to depend a little bit on your specific situation, but some essential parameters that must be included with any water supply project are turbidity, specific conductance, or total dissolved solids, and then bacteria. Those are the big ones that always need to be included. If you have if there's some historical information or you've reason to believe that arsenic and fluoride could be naturally occurring and need to be analyzed, it's important to analyze those as well. I would recommend always doing that analysis, but if you have strong reason to believe that you don't need to worry about it, for example, this is more common in wells, so if you don't think that you need to worry about it, then it's not something that you would necessarily have to analyze. And then some other supplemental water quality characteristics that are just always good practice. It's important to know the pH, temperature, alkalinity, dissolved oxygen, and iron. pH, I've seen that come up as an issue because it's low enough where there's a risk of corroding the pipes, and so it limits the type of pipes you might use. And then lastly, if there's human activity that you're aware of, so if in that larger watershed area, if there are latrines or agricultural land where nitrates might be used for their fertilizers or phosphates, it's important to run some tests on that to see if it's a problem. Nitrates in particular, I think its value of 10 parts per million is what can prompt blue baby syndrome, which is something that you obviously want to avoid, and so you need to be aware. Maybe there's not bacteria, but there's some nitrates from some agricultural fields nearby, and so you certainly don't want to make that a new water quality concern for the community. Again, more information on the water testing guidance sheet. So this looks like a very dense slide, but there's just some additional activities that you should be doing, and different type of information that you need to collect in addition to just that water quantity and quality, all as part of that initial assessment, all a part of just this very first step of picking what the best source is. And really it might seem like a lot for that first step, but really that first step is almost the most important one of a water supply project. If you're working with the right source, then you're going to make good decisions moving forward. But if you get caught trying to make something work with a source that's just not the best option, you can just be, your project will be riddled with challenges that will be hard to overcome. So in addition to the quantity and quality of the source, understanding the elevation of that source is so important to know if gravity-fed option is available. And so you have to plan on doing some sort of survey. The type of survey might depend on the level of accuracy that you're needing, at least for that initial assessment. But you should always plan on surveying the land early on to get a sense for what the elevations are of the source, a potential storage location, the highest house in the community, the lowest house in the community. Having too much of a difference between elevation can also be a problem. So you need to have a general understanding of the feasibility of a source based on the elevation of those features. Understanding the local laws and regulations is extremely important to understand. In certain countries, there's standards of what the per person demand needs to be. There's standard tank designs that all the local contractors use, and so you need to be aware of those so you can make sure that what you're doing is appropriate in the context of water projects in that country. We talked about the importance of the land ownership and knowing that you have permission to use a certain source, and then also knowing what those future development plans are in the community, so that you can make sure, for example, aside from making sure that there's not going to be new houses, upgrading of your source that could be a source of contamination, but also making sure that you understand that the beneficiaries, the people that live in the land around it are maybe beneficiaries of the project, so they're going to be more likely to be willing to protect that source in the future. It's also really important to visit hardware stores so you can make sure that any material that you're using is locally available. That's a flat-out requirement of any EWB USA project, that all materials are locally available. And so you need to be aware of what materials are, and this is especially important with any kind of pump option or treatment option. If it's not locally available, it's going to be really hard to fix if something goes wrong, and therefore it's not going to be sustainable. It's important, too, to characterize the types of soil, especially for any foundations that you might be needing to design. I suppose this is more applicable for a tank storage design, but during that first assessment trip, even when you're at that point of selecting a source, it's important to understand the types of soils at the project site so that you can understand how to design the foundation of whatever structure. One of the things that I think chapters that are successful find time to do is to simply go around and visit other water supply systems in the region or in the country. This certainly will never be the first water supply project for any country, and there's going to be all kinds of examples of successful and failed projects right in the vicinity where you're working, and so you should familiarize yourselves with those so you already know what seems to work well and what doesn't. Learn from those lessons of previous projects. And then spending time to survey the community members to really understand what their perceptions are of the projects and expectations of what the end result is going to look like, and then an understanding of what they can afford really should be driving what source option you're even going with. Sometimes the community members, they know, they've already kind of done this analysis, and they know exactly what source is the best, so maybe what you're doing is more confirming that what they are assuming is correct based on the additional testing that you can do. And then getting some general dimensions and measurements of the source area, the potential depth a well might be, the width of a stream if you're going to have to build a dam. Just some physical measurements are important to do. And then lastly, on your assessment trip, even for the point of just selecting a source, pictures are so helpful when you get back in the States. During an assessment trip, you can be just jam-packed trying to get all this data, and you're taking in so much just culturally aside from the technical data collection. And so having a bunch of pictures to go back and look at can really help as you're trying to process your different options. So, we've talked about just a ton of different data that you would need to be collecting just all for the first step of picking what source is the best. And so to process all that information can be very challenging. And so that's one of the main reasons why we have a new report in our reporting process, which is referenced down at the bottom here, the 523 Alternatives Analysis Report. It's so important to really do an objective analysis of the different source options, considering all the different factors that we've talked about, so that you can be very confident as you move forward that you're working with the best source. And so this is just an example of how you might go about doing that kind of analysis, but there's all kinds of different ways you could approach this. But here's just an example where you have the different source options. In your community you might have Upper Spring 1, Upper Spring 2, and rainwater, because drilling is just not an option. But you put your different sources here, and then all the different factors that you want to, your evaluation criteria are along these column headings, and then you can kind of come up with some sort of ranking, good, bad, okay. I've seen color coding or I've seen in each box is just a description of the water quantity at this location. I guess quantity is a pretty easy one to quantify, but O&M requirements, just maybe a description here, so that you have this nice table that hopefully will allow you to see objectively which source option is the best. And so once you've done that, and this is really kind of the first half of the presentation, is just all the things you need to consider to pick your source. Once you pick that source, the next thing to do is figure out how you're going to develop that source. Or what I mean by that is, are you going to need to build a dam, or are you going to drill a well, or are you going to do some sort of spring box? How are you going to actually capture that water to make it more available, whether it's through infrastructure or point of use, whatever that end goal is, it might depend. But the remaining portion of this presentation is to just go over the different pieces of infrastructure and just some design considerations to think about as you're going about each one. And so the first one is a dam. And so this is what you're going to need to design and include in your design a detailed drawing and specifications for a dam. And so this would be appropriate if you're going to collect water from a decent-sized stream, where you need to have a system for damming up that whole body of water and allow for overflow during those high storm events. And so this is just kind of a diagram of a dam you might have made of concrete, where this is actually a picture. I don't know if you can really see it, but this is the before and this is the after. And there's an actual dam right here that I'm pretty sure, if I'm remembering this project well enough, that it's just a dam that was made of, I think, sandbags or something of that nature versus an actual concrete dam. But so, like I said, I'm not going to go into details about how to design a dam. That's really what we would be relying on your professional mentors on your teams or your technical leads to be helping you with. But just some things to consider with your design is, again, being aware of the variable flow rate, making sure that your outflow is not too high so that in the base flow condition no water flows out of it, making sure your overflow is big enough to handle those large storm events. Understanding if debris could be an issue, and how, if you need a screen or something to protect from debris entering into your water system. We talked about overflow cleanouts. Erosion control and bank stability, that's really important. You want to make sure that you don't create a dam and then all of a sudden the water is going to start flowing around the dam, or you're not going to have some erosion problems upstream or downstream of that dam. And then, understanding where that exit point is for the outflow pipe. And then, the feasibility of actual construction. During construction, are you going to have to divert this huge body of water that's going to be really challenging in and of itself? That might be something that limits your ability to dam up a particular source option. And then the next one is this bankside intake, and really it has all the same design considerations as a dam. It's just a slightly different setup where you're not actually damming the whole river, but you have some sort of side bank intake structure so that you don't need to dam the whole river. And these, again, they're just kind of schematics to give you an idea of what the construction would actually consist of. Here we have a spring box. This is an example of a spring box. Just a simple box that has a lot of the same considerations as the dam, the variable flow rates, the overflows and cleanout. And back pressure alternate flow paths, this is something that I think is more unique to the actual spring box. You know, with a dam, you can kind of see the natural channel, and so you can kind of picture where the water is going to go as you dam it up and increase the height of that water. But with a spring box, it's really hard to see what's going on because it's all underground behind that point where the water is daylighting. And so it's so important to understand that water elevation in the base flow condition or the dry season so that you can make sure that your outflow is not too high. I know I worked on a project where you know, the contractor, when he was constructing the spring box, didn't really follow the design as much and put the outflow elevation, the pipe there, that elevation of that pipe at a slightly higher elevation than what was specified, which caused the water elevation to obviously increase until it could flow out of that pipe. But that created a situation where by increasing the elevation at that point, the water started flowing around the box. And then the flow rate that they needed could not be achieved in that community because the box was no longer capturing all of the water. And so it's really important to understand exactly what that elevation should be of the outflow. This next one for these surface water, and I guess the spring boxes could be surface water or usually it's groundwater fed. But in any case, one thing that I wanted to just take a second to focus on is that it's not just the hard infrastructure, the concrete work that is part of the development of that source option. It's also essential to really think about the protection of that source area. And so what does that mean for a spring or a surface water source? Typically it's something that involves no infrastructure and it's more of a capacity building kind of thing. But it's so important both with respect to the quality and quantity of that source to have a protected source. If that source is degraded, if the trees are all cut down in the source, that can impact, you know, increased erosion, which can cause more flash flooding and less storage in the watershed so that you don't have year-round sustainable flows, and then it also can create more runoff with more contaminants and have a water quality problem that you didn't have before. And so understanding how to protect that is important. And for our purposes, you know, really the first step is just figuring out what is the drainage area. Take some time to walk up and see the drainage area. I know I've been surprised a few times where I walk up to a source and it's this beautifully protected, you know, all these great trees. It looks perfect, and then you hike and it's just, gosh, sometimes the forest is so dense that you don't even see that 50 meters up gradient or 100 meters up gradient. It's completely deforested and it's used for agricultural fields where chemicals are being applied. And so it's important to just kind of walk up and get a sense for what's going on higher in the watershed. You know, this here is a situation where this is the capture box, and if you go up the drainage area, here's all forested area. But if you walked up a little higher, you can see that this land is actually used for agriculture. And I think if I remember right, there's pretty steep slopes along here, and so there's a huge potential for sediment loads, which I believe is a problem at this source intake here. Sometimes the solution might just be, you know, fencing off the source, the immediate area. Maybe it's forested here, but you need to put a fence around the actual source area just to eliminate people going to actually use this water and doing bathing and things right at the source, which is the source of contamination. Sometimes it might be necessary to have some conversations with the local government to just get an understanding for the potential to protect the source. You might be surprised that the government or the local municipality would be in support of protecting a different area, you know, around the source area. And then a lot of times the biggest thing is just to have a system set up where people are responsible for walking up into the watershed and monitoring the situation so that if there are trees being cut down or if there is something going on, they're at least aware of it to then begin to think about how to solve that problem. And then the last important thing to think about is just education, education, education. Sometimes you find the community knows more about the protection of that source than you ever will, but sometimes it's important to gauge that, and you might find that there's a need for some education on the importance of protecting that source and the impact of certain activities on that, and the whole kind of fate and transport of the contamination, which can be somewhat complicated to understand, but I've seen some good educational activities to try and promote that awareness. And then again, the land ownership and legal issues. If you have landowners who are not cooperating, then you're going to have a really hard time keeping that source protected. You might always be battling contamination. Rainwater catchment. So what's all involved with the rainwater catchment design? These can be fairly simple designs. It requires that you have a good roof that can actually collect the rain. Some design consideration is, aside from the roof, which I just mentioned, is making sure it's a suitable climate. Again, if you have a dry season that lasts a really long time, you're not going to have enough, the storage you would need to provide water during that dry season would just be enormous. And so it just is not an option based on the climate. You need the clean capture surface. So not only does the surface have to be of a material that's impermeable to collect the water, but it also needs to be something that can be kept clean. Storage is always required for it to be of any use. The first flush unit is something that I don't know if I've ever seen a rainwater catchment system design that didn't have a first flush unit, and that's really just an attempt to improve the water quality, because the most contaminated water from a rainwater catchment system is the rain that happens, just the start of the rain event. So dust or bird poop or whatever accumulates on a roof, and then when it first starts raining, that gets washed off, and then it's a clean surface, and then the rain continues, and then you have cleaner water. And so just capturing and discharging that first bit of the storm needs to be captured so that it's not entering into the tank that's then used for drinking water. So that's what the first flush unit is. And they're really a simple design. This is a little schematic of, it's really just a little float that once your volume fills up, it plugs off, and then water starts flowing to your tank. And so that's what that's about. And as far as designing that, how big this volume needs to be, I've seen in my reviews anywhere from 0.5 millimeter to over 2 millimeters for what is the assumed volume that needs to be captured before allowing water to flow to the tank. And I think it depends a bit on the how long between rain events you would be expecting, the type of contaminants you might expect to see on the roof, but that's kind of a general range. And I guess there's this website down here that might have some good information on doing that kind of design. This next one is fog collection, which is something that I have not seen a fog project at EWB USA, but essentially it looks like there's some sort of screen where the fog accumulates and you're able to collect water, and I have no idea what kind of quantity you could ever expect to get out of that and if it would be sufficient for a community scale kind of water system, but nonetheless we thought it was important enough to mention to see if it might be appropriate in your situation. So the wells. Wells can be take many forms, and then it introduces the potential need for pumping. This first slide is a slide of an open well, and open wells are basically holes in the ground open to contamination from the surface, and water generally is collected by some sort of hand bailing or kind of rope pump to access the water. And I don't know that I can think of any EWB USA projects where the design is to dig a hand-dug well that's an open well, maybe a hand-dug borehole, but not an open well like that, because it is so at risk to contamination. And so more often than not, an EWB USA project might be, there is this big open well and people are dipping buckets down and it's introducing contamination. And so I don't know if you can see so well, but this is a capped, there's a concrete roof essentially on top of that open well with a pump so that nobody's putting their buckets down into that well. And so that might be an EWB project. If you were to construct a new open well, the design considerations or the things to be a little worried about is just the construction hazard, depending on how deep you're going. And any excavation that's beyond 3 feet, there's this potential for collapse of the soils that, if it's above the height of a person doing the excavation, that's obviously very dangerous and something that we take very seriously, and you'd have to have a plan for that. And again, the issues with the water quality is always a concern with open wells like this. And so typically they're in the center of town, and so that makes the problem even worse, that it's hard to just manage the land around that area and limit activities that might cause pollution. So what seems to be more common is some sort of borehole. So you have an opening that's smaller and it's covered, and a hand pump, usually something has to be installed to pump the water from this well. It's not something wide enough where you could dip a bucket down into it. So you have some sort of pump that goes along with this well. And so there's a lot of design considerations for a borehole. For one, you need some sort of hydrogeologic study. But any kind of drilling method for a borehole is going to have some cost to it, and sometimes that cost is such that you really need to understand if there's a good chance you're going to get enough clean water out of it to make the investment worthwhile. So you need some sort of hydrogeologic study. In some countries, they seem to have local hydrogeologists that sometimes you can contract out the work. Some chapters have hydrogeologists on their team and can really do a good investigative assessment to get a good judge of whether or not there will be a lot of water. Sometimes you have to really spend a lot of time talking to different drillers in the area. It can be challenging, but you do need to have some sort of hydrogeologic study to make sure that it's worth the risk of drilling a well. Sometimes you might drill a well and it doesn't work, and so you have to go poke another hole to find water, and so it can be challenging if you're stuck having to hunt for water. It requires, I don't know if I can think of a single EWB USA team that has drilling expertise on their team, and so you're always needing to contract that out with local drillers who are familiar with the local methods. And so you need to get to know these local drillers and figure out, who would be appropriate to drill your well and what kind of qualifications do they have, and will you be able to have some sort of contract. I've worked with a chapter who the driller they didn't have a good enough contract, and the driller didn't do a great job, and the chapter was kind of stuck with a well that wasn't usable. And that seems to come up more and more, and so it's really, really important that the driller you're working with you have confidence in, and that you have a contract so that you have something to hold them to. If you can get some qualifications or references on drillers, that's even better. So you might drill the well and you get enough flow, you're happy with the flow, but you find out there's an arsenic problem or some sort of problem that's harder to treat. And so you need to be prepared for that and make sure that if you're going down that path, you would be able to address whatever treatment needs might be needed. Again, you have the risk of contaminants. Even, hopefully if you're going in a borehole, you can go a little deeper. Maybe you're going through a confined aquifer so that you're a little further away and it's harder for the contaminants to get down, but you still would need to consider source protection, and I have a slide on that in just a bit. And again, you can't quantify the quantity and quality of the water until after the drilling. So you have to decide as a chapter if you can afford to drill a well and make a change in your project if you find out that you can't get the quantity and quality you need, and you need to go through a different source, and you need to at least be prepared for that consequence no matter how much you're doing to try and prevent that situation. And so again, there's a variety of different drilling techniques, and it just depends. You can have this huge auger here that's something that a truck comes in, or some more hand drilling techniques. You really need to figure out what's the local practice and get to know those drillers. You're not likely going to be able to introduce some new drilling method unless you really have that expertise as a team. So a lot of this is just figuring out what the local practices are and working with that. And one thing that I think a lot of times doesn't happen, and this really highlights the importance of having proper oversight when the drilling work is being done. So even though you're most likely going to have a local person do the drilling and they're going to be contracted, you're going to need to have some oversight of that. And one of the outcomes of that oversight is that you should have something that looks like this, a well log, where you know what the soil, the formation is like at different depths, so that you can really understand where the screened interval might be in your well. You can run some analyses to figure out what kind of flow rates you could expect to get based on the formation and the well diameter and the screen. And a lot of times I found, after a well is installed and maybe the chapter wasn't there to oversee the entire installation, and there's a problem. There's a lot of sediment in the well. They're just not getting the flow rates that they expected to get. And to kind of troubleshoot the different options, having a bore log like this is just essential for kind of trying to understand what the situation might be and how to fix that, to kind of start narrowing down the options. And so being there to make sure that the driller does this, or that you might have the qualifications to put together a bore hole log, is essential to make sure you don't have problems later on. It seems that I'm working with a couple chapters just right now, so maybe that's why it's fresher in my mind, where they have a lot of sediment in their wells, and they don't know why. They're not sure if it's just a problem with the aquifer itself. They don't know if maybe the right screen was not installed, and so there's sediment getting through. They don't know if maybe after it was installed and during the development process, when you're pumping a bunch of water to make sure that you're pulling the true clean water from the aquifer, maybe it wasn't developed properly, and they just don't know because no one was there and the driller is not cooperating after the fact. And so having that oversight is just so important so that you don't find yourself in that same situation. And then one last slide on this borehole. There is a design that goes along with the well. Sometimes chapters say, oh no, we're going to install a well and we're using this driller, and that's all the information that's provided. But there is an actual design that you need where you specify the casing, the type of screen, the screening interval, specify that there'll be some sort of well pad, or what the sanitary seal is going to be, what's the space between the borehole and the well going to be to ensure that you don't have contaminants coming in from the surface and down into the water. And then the procedures for developing the well to ensure that it's clean. So there is a design involved with that well construction. And then wellhead protection, just like we talked about surface water protection, wellhead protection is extremely important. You need to make sure that there's certain setback distances from that well. I'm not going to give you a specific number you should use, and a lot of it depends on what the geology is there right there, but a rule of thumb that I've seen some of the technical advisory committee members use is 75 feet to keep away from any latrines, livestock, manure, septic tanks, any source of contamination. It's always best to understand the groundwater flow and make sure any sources of contaminations are down gradient, but at least having some sort of radius around the well that there's no activity is important to ensure protection. A bored well is going to be better than a hand-dug well for contamination, which we already talked about. Making sure that it's capped properly so that contaminants aren't entering, you're not creating a new path of contamination into the aquifer. And then also making sure that you're properly decommissioning any old wells, which can be paths of contamination, or latrine pits, which can also be a problem, even if it's an abandoned latrine. Making sure that understanding what's in that pit and that it's not directly connecting to the aquifer is important. So I think the next several slides are about pumping. So we've talked about different wells, and sometimes you need pumping for even a surface water source that's down gradient from the community, and then a lot of times it's just with wells. There's tons of different pumps out there, and I have several slides that kind of go into the details and the pros and cons and costs of each pump. And I don't want to spend too much time going through those in detail, but I just want to highlight them so that you're aware and can revisit this presentation as you're looking at what's most appropriate in your community. And so here's just a list, rope, hand, surface mount, submersible, ram, and wind. These are all different pumps that might be appropriate in your particular situation. And here's just, I guess, some pictures. Here's some sort of, I think it's maybe some sort of wheel pump. What was the last one? This is the merry-go-round pump right here. This is some sort of motorized pump. This looks like a ram pump. I can barely see this picture, but I believe it's some sort of pull. Oh yeah, this is the rope. This is the rope pump. This is the next slide that kind of goes into the details of a rope pump, what it consists of, the potential costs, the capacity that you might expect to achieve, the flow rates that you can expect, and then a website that you can go to learn more. And then just some benefits. It's low cost, doesn't require electricity. It can be locally manufactured, and it's established technology in some regions in Latin America and Asia. And then some constraints is that there's a depth limit, which is common of most pumps. You always need to know what the maximum depth is. It requires manual labor to actually get the water. Ropes break, and I guess that's kind of a problem or a risk with all pumps, is that all pumps break at some point, and so you have to have a plan for fixing that pump or paying for a new one. And then the design precludes thorough well capping, and so that can be a problem because then it's a source of contamination. So that's a rope pump. I'm not going to go into as much detail on these next ones. Here's a schematic, another variation of a rope pump, some pictures of projects. Next one is a hand pump, and I'd say this is probably the most common. Well, this is just one particular hand pump, but just hand pumps in general are the most common for EWB projects in situations where they can't afford electricity or there is no electricity. And there's a whole variety of different hand pumps, and really what it's going to come down to is what are the locally available options and what kind of success rate do those locally available options have. Because you're not going to be able to ship a pump from some other country, and so you really need to understand what's locally available, because even a simple hand pump is going to break at some point in time, and you need to make sure that there's the expertise in the country to troubleshoot and fix that, or buy a new one if they need to. They need to be available. And so, again, I'm not going to go into detail here, but various hand pumps are appropriate depending on the specific needs of your community. And here are just some pictures. That's the play pump, or the merry-go-round pump. And then a surface mount pump, which is a small pump at the ground surface, and it can be used to lift water from superficial aquifers. It can raise water pressure in a distribution system, move water in a conduction line to a storage tank at a higher elevation. And this can be powered with some sort of generator or being connected to the grid or some other alternative energy source. The cost may be a little bit more expensive than some hand pumps, but not as expensive as submersible pumps, and it has its own limits with depth and appropriate uses. And again, it's going to come down to what's available locally and what does the community have the capacity to maintain. Submersible pump, it's also an electric pump, but it's one that you actually put down into the well. It's usually a little bit more expensive, but you can draw water from a deeper depth. Ram pumps, this is a pump that you're using the energy from some water supply. So it kind of has a hydroelectric capacity. You're not converting it to electricity, but you're just taking that energy from the water source to start pumping. And so the key here is that you need a pretty good flowing body of water to produce the energy you need to pump even a small amount of water for the community itself. So you need to have some sort of stream or some good source of water flow. Just a schematic of the ram pump. Some more pictures of a ram pump. Wind pump, you're just using the wind energy for the pump itself, and this is not as common because a lot of times people just don't have, well, for one, it's expensive and takes quite a bit of work to do the windmill, but then also a lot of times you just don't have the wind data to design a wind pump, or you just don't have the wind you need for a pump like this to work. But it's still worth mentioning. I don't know if I can think of any projects at EWB USA with the wind pump, but there might be one out there. And here's a website on the site too. So pump sizing and selection, the main thing here is just, you're going to have a certain flow rate and you're going to have some elevation, some head requirement of your pump. And once you know those two things, you're just going to have to look at what's available locally, and you're going to probably be dealing with a small subset of total pump options out there, especially if electricity is not an option. And you're just going to have to go from there with your different pump options. This is just a slide of a pump curve to show you what you should expect to see from a pump manufacturer so that you can understand and make sure that for the specific flow and head requirements that you need based on the elevation and the demand of your community, flow demand of your community, you can make sure that you're picking a pump that meets that with the best efficiency possible. And so any pump has these pump curves, and that should be something that you're looking for and will eventually have to be a part of your design. The power, the other key piece of a pump, well, for an electric pump in particular, whether it's you're also involving wind or solar or hydro to get it, but that you're eventually converting it to electricity, is that you need some sort of electric design. And I think this is one thing that chapters overlook until they get to the point of the final TAC presentation. But you really need to understand the wiring. And I'm not an electrical engineer by any means, so I wouldn't be qualified to do an electric design for a pump. But it seems that a lot of times people pick a pump, they know the pump vendor they're going to use, and they're going to install it, and it's just going to be installed, and that's all the information that's provided. And so you really need to understand who are you going to use, a local electrician or a local electrical engineer to do that connection, and if so, what is their design, and have you seen that, and is it appropriate? Or do you have somebody on your team that can actually put together that electrical design for that pump connection? In either way, it can be addressed, but it does need to be addressed where you need to understand, is it single phase versus three-phase electricity? What kind of grounding is it going to have? What kind of automatic switches is the pump going to have? What are the limitations so that your pump doesn't burn out? All those details need to either be accounted for in your design, or you need to have reviewed the design of somebody else so that you can ensure that you're not going to have those kind of problems. And again, I see that this step is a lot of times overlooked, and at the TAC presentation, the final presentation with your technical advisory committee, it becomes an issue. So it's something to think about up front and not overlook. I know that I worked on a project where, the project was at the point where the pump was being installed, and it was, I think it was a three-phase pump, even though the source electricity was single phase, and so obviously that was a big problem and required a lot of delays in the project. It's also important to think about the housing of the pump itself, where it's going to be placed, how is it going to be protected to ensure that it's not going to be at risk for theft or vandalism, that you're not having to worry about it. It's not in an area that's going to get flooded and damaged that way. I've worked on a few projects where that's happened, where the pump was along the side of the river and a big flood came and the pump got carried down the river, and so they had to start over the project. So there's a variety of different things to consider just in the placement itself, and if there needs to be some sort of housing, and if so, the spacing, so that you can repair the pump as necessary. So the last couple slides are just focusing on some lessons learned, and I'm not going to, there's a lot on this slide. Again, it's something that might be appropriate to look at in more detail later, but I think most of the things I've hopefully touched on throughout the presentation, and the purpose of this is just to highlight them. There's a few on this slide, and then I'll go through some specific examples. But again, just the importance of doing a source selection process to begin with is something that's key for a successful water project, which I think I've highlighted already. Making sure you're collecting all the data you need on your assessment trip. Sometimes chapters find that they can't collect all the technical data that they need on one assessment trip, especially considering on your first assessment trip, it's the first time you're getting to visit the community and understand some of the non-technical aspects of the project. And so it's really important to think about the potential of having two assessment trips in case you need to collect all the data you need just for that first step of selecting your source. The supply demand is critical and needs to be done during that source selection process. Seasonality we've discussed, land ownership we've discussed. A memorandum of understanding we haven't discussed as much, but that's just a contractual agreement that has proven to be very valuable with projects, especially with drillers, some sort of contract, to put things in writing to make sure that everybody truly is on the same page with who's responsible for what and who's contributing what to the project. the technical abilities of the community and the affordability of pump or system operation is essential to think about up front in the source selection process. Making sure you have some sort of water board, and I think that this will get talked about a little bit more in the subsequent water supply presentations, but in the first assessment trip it's important to lay the groundwork to ensure that there will be some governing board who's responsible for the water project and the fee collection. No matter what the water project consists of, there will need to be some sort of fee collection because it will need to be maintained and there'll be a cost for that maintenance. And if there's not fees being collected, it won't get maintained and it's not going to be a sustainable project. Community involvement in all the decisions that are made, the source selection process, I didn't really talk about it too much, but it's really important that the community is helping you through that process, identifying the sources, evaluating the pros and cons, and ultimately all the decisions should so that they can make good decisions. But as much as possible, the community should be making the decisions because after all, it is their project that they need to have a sense of ownership with so that it has a chance of being sustained. Security options with the pump we mentioned, and I guess maybe I should just highlight that there are EWB USA projects where pumps have been stolen, and so it is something that happens and it's important to plan for. And then locally available materials, which we talked about. So just a couple examples. I believe I actually maybe already talked about some of these examples. This first one is a spring box in Honduras where the outflow of the spring box was set higher than the base flow elevation, and it caused backflow, and all of a sudden the community wasn't receiving the flow that they needed to just meet the average daily demand. This next one, the Bolivia rainwater catchment, is just an example of an insufficient understanding of what the actual demand was of the community, and so they had done this system. It was dry for 2 to 3 months a year, this rainwater catchment system, but they thought there'd be enough storage, and it turned out that it didn't come close to meeting the demand that the community needed, and so it essentially was a failed project. Solar pumps, solar panels are expensive and flashy, and people know that they're worth money, and so they get stolen. And we've had that happen on EWB USA projects, so it's so essential for any solar panel project, well, first to make sure that the solar panels are available locally, because if they're not, then there's no chance that they're going to be replaced if something goes wrong. But aside from that, making sure that you've addressed the potential for theft, damage, making sure that they're not in an area where kids are throwing rocks or potentially throwing rocks that could damage, and that the replacement costs and any costs associated with the operation and maintenance and replacement of those solar panels if something goes wrong needs to be incorporated through fees that are collected by the community, or that there's not a chance that it will be sustained in the long term. Nothing's maintenance free. And then this last example is another one that I already talked about, where the dry season flow, to highlight the importance of the dry season flow, where it wasn't measured. They used wet season flow, and then the project, after Rotary had donated $80,000 towards it, had to be redesigned. And then these last lesson learned are just they're just characteristics of what we've seen here in the National Office as we review these designs as being successful with projects that are implemented as EWB USA. And I'll read through them and only highlight anything that's different. This first one is somewhat different, and that is to make sure that you always have a locally engaged partner. If we have a huge limitation as an organization by the fact that we're based in the U.S. and we spend a few weeks a year in the community. And so without somebody locally who's really engaged in the project and can provide information, we talked about so much data that's needed. If you can have somebody locally helping collect some of that data in your absence, you're just at you're much further ahead than other projects. And it's also important to get honest feedback as you're trying to set expectations with the community. If you don't have somebody locally there to help you get that data, it's hard to get honest information back. Really understanding the technical and non-technical aspects is key. Let's see here. Talked about a couple of those. Having, just communication is so important. It's such a challenge. Even in the U.S., working on a project, any engineering design I've done in the U.S., that process of communicating that to the local contractors and overseeing that and making sure your client's happy is a communication challenge, and when you add a language barrier, it's even that much harder. And so making sure you have things in writing and clear communication and good translators is just key to ensuring your technical project is going to work out. And maybe it's been highlighted, but water projects they're unique in the fact that they require so many different disciplines. We talked about hydrogeologists, electrical engineers. I didn't talk about it, but I should have. The fact that a lot of the concrete structures require structural engineering, especially a water tank, geotechnical analysis, water resources engineers, public health people, since again this is all part of a health improvement project. And so making sure you have an appropriate team for your project is important from the beginning to ensure you have a chance of success. Talked about the water boards, and then having a plan to return to your project after it's constructed to monitor it is also important, because more often than not there is some tweak that's needed after that first monitoring trip. And so providing that long-term commitment and ensuring that the system works is also key for a successful project. Thinking through the construction is important, and involving the community. That we didn't really talk about it at all, but hopefully in some of the other technical webinars, just construction management and construction planning is so important given the limited amount of time you're in the community to actually oversee the construction of a project. And so having somebody on your team who has a good sense for that and being realistic and planning for delays is really important for a successful project. And so the next slide, well, I guess I thought there was I guess it must have been deleted, or it's part of the second or third water supply project. We used to have a list of some good references to use, and so I believe it's in that water supply or water treatment presentation. So look for it there to get some general references, websites, books to use as you're working on your water supply project. And then this last slide just has my contact information. So I realize that it's a lot to cover. I probably covered some things in too much detail, other things in maybe not enough detail. And so if you have some questions and you don't believe that they'll be addressed in the subsequent webinars, please don't hesitate to email me, and I will do my best to answer your question or put you in touch with somebody who can. And that concludes this webinar. Thanks so much for your time.
Thank you very much, Kelly, and thanks to our participants for your attention. I want to take this opportunity to once again remind our participants that you must complete and submit your attendance on the following webpage to receive credit for attending this program. This concludes today's program, Water Supply Part 1 of 3, Source Selection and Development, brought to you by Engineers Without Borders USA and Contract Solutions Group. Please check our online catalog for the latest instructional programming from EWB USA and Contract Solutions Group. This program is copyright 2010 by EWB USA, all rights reserved. Thank you for joining us for this program, and enjoy the rest of your day.